Okay, we continue with a case in which we've got two nominal variables, and we want to estimate the effect of those variables into a numerical variable. And in the previous video we saw the parameter estimation approach. Here we're going to see the model comparison approach. Two approaches, maximum likelihood and Bayes factors, and it is a between subjects design. Okay, so let's maximum likelihood. I did the analysis with R. Basically this is model 0, which is a null model, and that is the same as in previous analysis. So basically in order to estimate to determine the likelihood of a reaction for each reaction time we observed in our sample, we use a normal distribution with a mu for each prediction. So the mu is the prediction, and we use only one standard deviation in that normal distribution. These two parameters are estimated, but in the null model, model 0, mu's is only one value, beta 0. And we know that the estimation of this one would be the mean of reaction time, the mean of all the observations we have of reaction time. So the prediction will always be the mean, and it won't be a very good model. It will have a low likelihood. So hopefully the other models have a higher likelihood, and this part of the model is exactly the same. The mu, the calculation of the mu is different. Instead of having just the beta 0, we add beta 1 and beta 2. Now we are going to use 4 models. One will have beta 1, we'll estimate beta 1, but we'll fix this to 0. So basically it's like not using this part of the model. Model 2 will estimate beta 2 and will not use that part. And model 3 will have beta 1 and beta 2, so it will estimate both variables. And we have another model which introduces a beta 3 that is not shown here, which is the interaction. So basically the interaction of two variables, and this is the new component that we didn't have in the previous videos, in which we saw the analysis of only one nominal variable. So now we've got the effect of one variable, the effect on the other variable, and the interaction between these two. And what's an interaction? An interaction is an effect on an effect. So basically is how the color variable affects the effect of the variable match on reaction time. Okay, it seems very difficult, but I'm going to explain it in an easier way. So basically in this case we've got an effect of match on reaction time. Basically, let's say we say that match, when there is match, the reaction time is reduced. Yes? So we expect the mean of reaction time when there is match is going to be lower than when there is no match. That is the case if there is no interaction with the variable color. But if match and color interact, that means that the effect of match on reaction time when we use black and white images in the learning phase will be different than when we use color images in the learning phase. Okay, so we may have an effect of match on reaction time when the color is black and white, and we may have another different effect when the color is color. So that is an interaction, an effect on an effect. And basically, if there is no interaction, then the overall effect of match on reaction time will be exactly the same in both levels of the variable color. So it will be the same with black and white images and with color images. Okay, so that is the interaction, and the implementation of an interaction in a mathematical model is to multiply the two variables. Actually, the scores of match and the scores of color are multiplied, and that is a new variable, and we are going to use that variable, treat that variable as a variable on itself, and we are going to estimate the effect. Now, remember that beta 0 would be the intercept. So meaning if the values of match and color are 0, so basically no match and black and white, that would be the expected reaction time. Beta 1 tells us, well, the extra reaction time we expect if we go from black and white to color. Sorry, no, this is the match variable. If we go from no match to match. So what's the extra reaction time we expect when compare the black and white, no match with match? Beta 2 is what I've been saying by mistake. How much we expect more when we go from black and white to color. And beta 3, which is this is the interaction, actually means how much we have to adjust in the condition in which match is 1 and color is 1, over the effect that we already calculated. So basically we have an effect of match, an effect of color, but we will have to add if the beta 3 is different than 0, it means how much we predict more in the condition in which color is 1, that is the value is color, and match is 1, that is there is match. And why am I saying this? Sounds strange. Well, because remember I told you that the interaction variable we are creating, we are multiplying the values of match and the values of color. So when match is 0 and color is 0 or 1, then the multiplication is 0. The same when color is 0 and match is 0 or 1. So basically we've got three cases, three combinations of values in which it will be 0. Only one combination of values we are going to get 1, which is match. When match is 1 and color is 1, multiply 1 times 1 is 1. So in that when we have 1, beta 3 times 1, so the beta 3 value will add to this equation. But when the interaction term is 0, then the beta 3 doesn't count. So basically that's what I'm saying. The interaction tells us how much we have to adjust in the condition in which the match and color, the value is 1 in both of them. Okay, so and now we've got 5 models, model 0 and the other 4 options, and we calculate the likelihood of each value of reaction time with the normal distribution. That's the same as before. The mu's of basically we are going to use one normal distribution per reaction time score, and we are going to use in those different distributions, it was going to be a different mean, which is the prediction that we get from this equation, but the sigma is only one sigma for all the predictions. Okay, so basically I did the analysis, and these are the best estimates for the parameters. So beta 0 547.2, which is that's the mean reaction time of the whole, taking into account all the reaction time observations. In model 1 is 531, and the effect of color is 25.4, so very small. And in model 2, beta 0 606 reaction time, and the effect of match is minus 117.8. So basically that means that we expect, when we go from no match, in which we expect a reaction time of 606.1, to match, we have to adjust by minus 117.8. So basically, in the no match condition, the mean will be in the match condition, the mean reaction time will be 117.8 milliseconds faster than in the non-match condition, which that will be the mean. And that's the best model, the model with the best AIC. Okay, so now that's the model comparison approach using maximum likelihood. Now I'm going to use the software JASP to do the model comparison with Bayes factors. Okay, so we bring JASP, and now we go to ANOVA, and instead of going to ANOVA here like we did before, we go to Bayesian ANOVA, and we've got as dependent variable reaction time and fixed factors color and match. And basically what we get is this table with the Bayes factors here. So basically the model with color over the null model is 0.3, so basically it's worse than the null model. And the model with the variable match is 90 times more likely than the null model. The model with color and match is 22 times more likely, and the model with color, match, and the interaction is 6.4 times more likely than the null model. Now, and this is actually what we do for hypothesis testing. We compare the model that we are interested in with a null model. So basically, if we show that is several times more likely than the null model, we can be confident that the null model is not a good representation of the data of the population. So and that would be it. And actually, when we get to hypothesis testing, I'm going to tell you that we just did it before. Now, in model comparison, we want to compare the other models, not just against the null. And well, we need to use a trick. And the trick is very simple. When we have the Bayes factors against, these Bayes factors are all of them against the null model. So when basically you obtain a ratio and the denominator was always the same, then the obtaining the Bayes factors between these two, obtaining a ratio between these two Bayes factors, or between these two, or between these two, or the others, it's equivalent to obtaining a Bayes factor between these two models. So when the marginal likelihood of two Bayes factors is the same, well, the ratio of these two Bayes factors is a Bayes factor. So that's what I did here. So the first row is the values that I showed before, is the marginal likelihood of the model color against null, match against null, color and match against null, and color plus match plus the interaction against null. So that's what I showed you in JASP. But we are interested in these comparisons as well. Well, basically, in order to obtain match over color, we obtain the ratio 90.2 divided by 0.253, and that gives us 356. So basically, the match model in comparison with the color model is the theta under this model is 356 times more likely than under the color model. When we compare the color plus match model against the color, is 94 times more likely. So basically, this means that if we have to use the variable color to in a model, adding the variable match increases the marginal likelihood because it's 94 times more likely. And when we compare color and match with interaction against color only, is 24.9. Now, when we do with this is telling us that color is not a good it's not a good variable to predict reaction time, because if we do 1 divided by 0.253, it will give us around 4. So basically, the null model is 4 times more likely than the color model. So basically, the variable color doesn't make any sense to add it. So when we have this information, then we only wonder whether we should include match, and obviously we should include match because it increases 90 times the likelihood in comparison to null. So let's compare these two with the two variables, and the two variables plus the interaction against match. Well, adding a color plus match is almost 4 times less likely than match, and adding the interaction is even worse. So basically, this is showing us that the best model is with just the match variable, and the color variable shouldn't be added to the model. Okay, so that's the Bayesian model comparison. And now we move to hypothesis testing. Okay, so first NHST, null hypothesis statistical significance testing approach, and then Bayes factors. But as I said before, we already did the Bayes factors in the previous case. Okay, so in NHST we have to do what we already been doing, but we haven't get to the ANOVA table. So let's bring JASP, and now let's go to ANOVA again, and we go to ANOVA, and the dependent variables reaction time, fixed factors, match and color. And here, sorry, that's the old analysis of the Bayes factor. Here is sorry, the analysis that we are interested in. Here. So basically, we've got the match effect sum of squares, the color effect, sum of squares, and the interaction effect, the sum of squares. This is the residual effect. So if we add the 4 sum of squares, we obtain the sum of squares total. And here, in terms of degrees of freedom, again, if we add the degrees of freedom, we obtain the degrees of freedom total, which is 119. Degrees of freedom total is 1 less than the number of participants. Okay, why is degrees of freedom here 1? Well, because we've got 2 values of the variable match, and the degrees of freedom is 1 less than the number of values, and the same with color, the same with interaction. Now, so the mean square is divided by 1, so we can obtain the same result, and the F-score is by dividing the obtaining the ratio between the mean square of each of these effects with the mean square of the residuals. And so the F value for match is 13.9, for color is 0.6, and for match and color, so we need to move that dot 2 places, so it will be 0.059. So very small F scores for color and the interaction, and 13.9 for match. When we obtain the p-value, this is less than 0.001, and these are 0.4, 0.8, so quite high p-values. So this, because it's less than 0.05, then we reject the null hypothesis, because if we assume the null hypothesis obtaining an F-score of 13.9 or more extreme, is very unlikely. The probability is less than 0.001, so we sort of reject the idea that that's true, and technically what we do is to reject the null hypothesis. Okay, so that's the null hypothesis testing approach, and the Bayesian hypothesis testing is what I said before when I did the Bayesian model comparison. Is when we compare to the null, we are doing a null hypothesis testing in a Bayesian way.